Hi everyone, how are you doing today? Good? Yes, thumbs up. All right. Class average is, I think, about 80%. So I was happily surprised, but I don't know what that means. So it means you guys are quite good actually. So maybe it was a bit too easy for you. I don't know. So maybe I'll make one or two things a bit more tricky in the final exam, but not too much, obviously. But I see that, yeah. So yeah, I think so. I made it a bit easier than the assignments. Thing is, math questions, it's just so easy to make things possibly complicated. So I was very careful. But yeah, I'll take that into account. Also, you had quite a lot of time. So probably for the final year, so the final is just 2 hours. So yeah, for the so obviously it's maybe it's going to be a bit shorter, but you have to be sure that you have time. Oh yeah. Oh, we can discuss this after the class about the midterm. All right. Okay, so people are getting connected. So about where we are in the class, we're actually doing good. I would say even too good. So what's happened there? What's happened is they have put the TD, so the class is just at the end of the week, and the TDs is just after the class. What this means essentially is you get no time to work on anything that we have done in the class that I could be asking in the next TDs. It's just 15 minutes after. So essentially what I've had to do is to always be faster 1 week in advance of what we would have been otherwise, which means that essentially we have almost covered everything we needed to cover. Yeah, 80% is the class average for the midterm. Yeah, I can't remember the average for the second assignment. It was quite good too. Yeah, so essentially you're too good, and I have to take that into account. Yeah, so in terms of material, so what's going on? Well, we finish chapter 7 today and start chapter 8, maybe even almost finish chapter 8, and then there's chapter 9. And so chapter 9 is optimization with a single variable. So for those of you who continue for the next class, then you're going to see again optimization with a single variable and optimization with two variables. So why are we seeing this? If you're going to see it again next class, that's because some of you are not taking the next math class, but still knowing how to maximize or minimize some function is very useful for you. So that's why we're seeing it right now. So what we're going to do after that, there is a small section in chapter which I have skipped, and I thought I would come back to it later. So that's what I plan on doing. And then I'm not sure if I'm going to add material or not. I'm going to see. And then certainly last class, we're just going to have some exercises to do in class just to prepare for the final exam. So that's how things are going to work out. Yeah, and there's so about the correction of the midterm exams. So there was some technical problems, so it's being done right now, but so probably over the weekend it's going to be posted, the solutions. Yeah, but so worry not, things went very well. All right, so without further ado, let us start today's class. Do you have extra question before or? No? All right. Okay. End of chapter 7. Underderivative. Oh yeah, and since we have more time, then I started again writing to you some quizzes to do in class. So that's going to be more interesting during the class. All right. So the last thing we had seen was partial derivatives. So just to state again, partial derivative, it's extremely simple. The only thing you need to know is, oh, if I ask you to take a derivative with respect to one variable, then you just forget about the others. You just treat them as constant. That's how you do it. So that's very simple. Now we're going to see two technical terms, but you shouldn't be scared by them. They are just names that we give to some objects that are useful. So the gradient. So what is a gradient? A gradient is just a vector of all the partial derivatives of a function. So for instance, for a function, let's say f of x1 to xn, then the gradient is noted with this nabla variable f of x1 xn and what I just store in my vector all the partial derivatives. So I'm just going to write them f1 to fn. So where this symbol there is an inverted triangle, is either pronouns del or nabla. By the way, I'm using parentheses to to have this this to show this. It's a vector, but we write it this way in a row fashion. So f1, f2, f3, f to fn. So that's the way we write it. So why do we need the gradient? So the gradient, so because it tells us a lot about where where a function is going. So it's when I want to optimize f, for instance, then it tells me a lot where I should go with f, given it the first derivative. So of course, so what we're going to see is that for f to be at extremum, so maximum or minimum, then it has to be that all of the partial derivatives are equal to 0 and some extra conditions in terms of optimization with many variables. But so that's one thing. And it's also very useful if for all numerical algorithms, because it really tells us the direction of ascent of a function. So, so let's say that is a fundamental object. Yeah, I could give you some example before that. So if I have f of xy equals 2x plus log of y, then this is going to be, oops. Somebody knows? Oh, my computer is unplugged. Oh, it's difficult this morning. No help there. What is the derivative of 2x with respect to x? Yes, thank you. And what is the derivative of log y? 1 over r y, yes. So this is the, yeah, let me write it. This is more, it's prettier. All right, so that's the whole thing. So if you see gradient, you just have to remember by heart what it means. It means a vector of all the partial derivatives. So if I have a function with two variables, then it's partial derivative first variable, second variable, etc. Okay, and as I was saying, it's a fundamental object for optimization. And it points in the direction of greatest ascent. So what do I mean by this? So I'm going to use a small drawing that I've done for a previous class. It's not perfect, but it gives the idea. So example for a two variable function. Okay, so imagine I have some function f of x, y, so two variables, and the f is a sort of cone-like shape. It's like look maybe like a this may look like a normal distribution, density distribution, and on the outside. So if I take the gradient at some point x, y, then since when I go in this direction, then I see that my function is decreasing. So when I increase x, it's the function is decreasing. So the first derivative is going to be negative. So it means that the gradient in the x direction is going to point this way. And in the y direction, so again, it's decreasing in this direction and increasing in this direction. So it's going to point in this direction. So the gradient is a vector. It's a vector of two coordinates, one for x and one for y, for instance. And it's going to point this in the direction of the maximum of the function. And one other thing that you can note is that the norm of the vector, so the norm, I haven't introduced this concept, but the norm is the length of the arrow there, is proportional to how steep the function is. So here the gradient is very, has a larger norm because the slope is steeper, and here it's smaller because it has this. And obviously, if I was very far with a very gentle slope, then the gradient would be almost zero. Yeah. So I could say it's norm. I'll just say length in quote is proportional to how steep the function. All right, so that's it's pretty interesting to see how it works, how we can represent the gradient in a 2D plane here in XY plane, and you see that it points in the direction of greatest distance of F. So that's the gradient. Question about the gradient? No. What unit is this? Oh, that's a great question. So here I didn't introduce any unit, but so it's in unit of F over, oops, yeah, of F over, so for the variable X, function F. No, let me just give you an example. So example. So yeah, expenditure equals to P1 X1 plus P2 X2. So partial of expenditure with respect to X1 is equal to here P1. And you see that, so it's in, so P1, so unit of P1 is of course dollars if you're in Canada, divided by yeah, so units, but so dollar is expenditure and units but is the unit of X1. So the expenditure, the X1 gives you expenditure dollars divided by the unit of X1. Can we say that the norm is equal to the, yes, okay. All right, so let's go there. So so this is something I wanted to talk about in 2 classes, but yeah, I can just introduce it. So the Euclidean norm yeah, I think it's written this way, of a vector X1, X2, Xn is defined as not so let me since V equals this, we write it V like this. And to be sure that we're talking about the Euclidean norm, we write it this way. And it's equal to, yeah, so summation of xi to the I take the square root of this. Yeah, so this is exactly this. And I have other norms. I can have this, or I can have this. So yeah, it can vary from 0 to infinity. So we can see that later on. Yeah. So these are all interesting concepts, but basically what it measures is it's a measure of distance. It's a measure of how far things are. And the Euclidean norm is the most widely used norm. It's something that's used all the time in something like econometrics. If you want to fit a line, so what's your tolerance about errors? Here you would have something like error terms squared. So what you want is to minimize the sum of the sum of error squares. But so for the Euclidean norm, we want to renormalize it by taking the square root. A norm is perpendicular to its vector. So a norm is not a vector, so you couldn't say it's perpendicular to the vector. Yeah, a norm is just a number. Yeah. No, but yeah. So maybe what you have. So something that I could say about the gradient, though, is that as you can see, the gradient points in some direction, and perpendicular to the gradient are level curves. Which are sort of indifference curves, if you want an economic version of it. So this curve here is represents the set of all points that for which f has the same value for the set of all points x, y for which f have the same value. And you see that the gradient is going to always point in a perpendicular direction to it. All right. So, anyways, we're ahead of what I wanted to discuss. So, but yeah, these are all interesting topics. Yeah. So, if you want to know what the unit of something is, so just write an example. So here, expenditure is in dollar. P is in dollars per unit. X is in unit. So if you take the derivative, D expenditure, DX1, you get dollars per unit. It's the same thing as if you were in physics or in chemistry, you have to make sure that the units are respected, and that's the same thing for here. Okay, so that's about gradients. Now, other topic, Jacobian. And the third weird name that you're going to hear later on, I think in next class, might be Hessian. But now again, we're just going to be talking about the Jacobian matrix. Okay. So what is a Jacobian matrix? Well, it's so if I have multiple functions, if I have multiple functions, then with the same variables inside them, so x1 to xn, then the Jacobian is just stacking the gradients together. So that's it. That's the only thing. So if I have f, g, and h function, for instance, then the Jacobian is going to be f1 to xn, then the next row is g1 to gn, then the next row after that, h1 to hn. So that's all there is to it. So that's a neat way of organizing all the partial derivatives. So that's for the intuition. So now let me give you a bit more formal. So given m functions of n variables, Jacobian matrix. Contains the partial derivative of n functions with respect to the n variables. So matrix can be of as a vector of m gradient of m gradient of length n. Yeah, so the gradients are of length n. Yeah, and it can be used. So partial derivatives gives us a way to test for functional dependence. Linear or nonlinear. Among a set of n functions. Of n variables. So I haven't said what I was talking about here. So this is simply, you remember that if I have a bunch of vectors of n length n, so the way to test for linear independence is to just put them in a matrix, n by n matrix, and compute the determinant. And if the determinant is non-zero, I know that they are all independent. And if the determinant is zero, I know that they are dependent or collinear. So this is a generalization of the concept to nonlinear functions. So that's why it's either linear or nonlinear. And here for the gradient, for the Jacobian, it can have a different number of functions and variables. But of course, for sure, if I want to test whether the gradients are independent among each other, then I have to have a square matrix. So I have to have the same number of variables and the functions. So let's take a two variable example. So I am going to have x1, y1 equals, if I'm going to write this way, so it's not that I'm taking any derivative here, it's just the name of the function of x1, x2. And then I have a second function with here the same number of variables. So y1, y2 equals f2 of x1, x2. Yeah, so each equation has two partial derivatives. So let's just say first order. Why? Because I can take many, derivatives many times. So first order is just taking a derivative one time with respect to either x1 or x2. Yeah, partial derivative. So there are two variables times two function equal for first order partial derivatives. So what you do is you take all them and place the Jacobian matrix. So we write it this way. So write it J equals to dy1 dx1 dy2 dy1 dx2, sorry. So you see that it makes sense with the definition of the gradient. So here we wrote it this way. So we had one function written as a with the gradient written in line, so in sort of a line vector. So here that's a good way to remember that you place the first function on the first row and then the second function of the second row. The partial derivatives are these x2. Yeah. And then if I want to test for linear independence, and I just compute the determinant of the Jacobian. So here I would get J equals this minus this. All right. So it's not that easy to see right away why you would do such a thing, because in a way, when we have vectors, for instance, then it makes sense to imagine, or is it possible to find a point of intersection for so if there are lines, for instance, then I want to find an intersection or not. In this case, dy1 dx1, dy1 with dx2, dy2 dx1, dy2 dx2. So they have all a specific value at a specific point x1 and x2. If I change, for instance, if I say, oh, they're linearly independent, they're linearly dependent, well, you just change the value of x2, for instance, and maybe then the first derivative are going to change. So it's really something that is local, because partial derivative or derivative in general are functions that depend on the value of the variable. Contrary to, so if you have f that functions that are linear functions, then in that case, obviously the derivatives are always the same. So they're always going to be, g is always, the determinant here is always going to be either 0 or non-zero. But if there are nonlinear functions, like this function there, then they could be 0 or at some point, but then it can become non-zero at some other point. But so why do we use this? Well, one use of it is going to be for constraint optimization of multiple variables, which you're going to see in the next class. But now that's something that you have to. I'm sorry if I cannot give you more intuition about this. Actually, I myself have not been using that all that often, so I can't really say that there is so much use to that. But yeah, here it is. So, all right. So just to finish this, if the Jacobian, the determinant of the Jacobian is 0, this indicates there is functional dependence among functions. That two variables change exactly in the same proportion with respect to some other variable. And of course, you can generalize it to n by n. Yeah, should I write this? Let's go ahead and let's write the n by n function real quick. N in case. So if x2 is n, 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 then the Jacobian is this. Yeah, you probably already have gotten the idea, but then I have n dxn. All right, so now I've just been talking for a while, so let's do some quiz that I started that I already made. So quiz. So, I'll put it in the chat. Or can you copy from the chat? I'm not sure. Oh, Patrick, you have a question? Or not?
Yeah. I'm guessing what I'm wondering in the 2x2 matrix, if the determinant is 0, we means the functions are linearly dependent. But in the m by n case, if we get the determinant equals 0, does that just mean that of the n functions we have in our matrix are linearly dependent, or does that mean that all n functions are linearly dependent of each other and we can't distinguish it?
So these are all vectors. So this is a vector of this is a gradient of the first function, gradient of the second function, gradient and the last function. And if the determinant is 0, then it means that it's possible to take one gradient and reconstruct it as the weighted sum of all the other gradients. So
Right.
it's like we've seen before.
Okay, yeah. But it's not possible to say which function is the dependent one.
Oh, okay. Which
if
function?
we were to eliminate it, then we would have determinant equals some other number besides 0.
Actually not, because imagine that I remove this. For instance, the last one, I think it's linearly dependent. But then what does that mean to remove it? So I still have to have a square matrix. So the only thing is to replace it with just a row of 0. But then you know that the determinant would still be 0 in that case.
Yeah. Right.
All right, so you can try your luck on this quiz. So I don't know how. Can you copy from the chat if I put it in the chat like this? Oh yeah, I think you can just click on it, right? This would be easier. Oh, sorry, I sent it just to Patrick. All right. So this is just tests about gradient, Jacobian, and linear independence. Oh yeah, and by the way, it's going to be easier for you if you have a pencil and paper. Yeah, so that's what we did today. We just started here, gradient and Jacobian. So to be able to do them, you have to have looked at the rules of derivation. If you haven't looked at them, then it's well, they're not too complicated, but
Sorry, sir. Would you mind scrolling a bit lower? Sorry.
oh yeah, sure. You tell me when it's good.
Yeah, that's good. Thank you.
So how many are we today? Yeah, I guess for the two last questions, I should have added none of the choices as a choice. Otherwise, it looks strange. Yeah, so let me add this. Anyways, that's going to be useful for later. Okay, so why don't we have a look? So is somebody still trying to do it, or? Yeah, I think we should move on a bit. So here we go. Let me share my screen. Okay. So what is the gradient of each function? So so the gradient of the f. All right. So I can't see the question. So here, f. So the derivative of f with respect to x is 1, and this is 2y. So at 1, 4, so 1 is 1, and 2 times 4 is 8, so it should be 1, 8. Yeah, so everybody got it. Second one, yeah, so few of you thought it was 1, 1, but I think the right answer is 1.25, so let's just look at it real quick. So the derivative with respect to, of log is 1 over x, and the derivative of log y is 1 over y. So it should be 1 over 1 and 1 over 4. Yeah, so it's 1 over 1 and 1 over 4 is 0.25. So is that, are we good about this, or it's now is the time to ask questions?
I guess I'm one of the people who screwed up here. I saw VG 101, so I didn't know which, like what does it is 101? It says row 2 on your screen. VG 101.
1 is the gradient. So one
Yeah, but I guess in your title here,
Oh, it was not.
it says
Oh, G.
1 1.
Oh, okay. Sorry. Oh, that's my bad. Actually, it doesn't make sense. Oh, sorry about this. I'll just change that real quick. Oh man. Yeah, because when well, okay, so real sorry. That was the thing I meant to write. Yeah, these look okay. All right. So sorry about that. I messed up. Thanks for Patrick. And then yeah, last one, everybody got it. And which function are functionally dependent? Okay, so this is all over the place. So none of them. So none of them is the right answer, but I didn't put it right away. And then the last one is G and H. So this, most of you got it right. So I'll just do it for G and H if you don't mind. So my questions was this. All right, so let us go back to the class. Okay, so have f of x equals g of x, h of x. So gradient of g. So over x over y, and then at 1, 1, that's 1, 1. And then the gradient of h is 1, 1. So at 1, 1, it's 1, 1. So obviously they are, so if we take the Jacobian would be simply J equals to x 1 over y 1, 1, and then at 1, 1, I have J is,
Is there a question?
yes.
So how come like at 1, when we plug the numbers like at 0.1 and 1, it should be half and half, no? The value 1 divided by 1, like.
So 1 over 1 is 1, and
No,
1
no,
over.
like in the other in the quiz. We
Oh
did,
yeah. So if it would be 1 over 1 and 1 over 4.
oh, it's 1 over 4. Okay.
Mm-hmm. So yeah, simple. All right. So that would be it. So for this chapter, so you see, it's nothing too crazy. The thing, of course, is learning all these derivative rules, which are a lot initially. And there's only one way to do it, is to just practice, and get good at it. But if I look at the result you get for your exam, I think you're quite good at it. So what time is it now? It's yeah, 10 to 10. So why don't we take a small break and then we start the next chapter, like in 10-ish, 12 minutes maybe. All right, we're back. So let us start an important chapter. Well, chapter 7 was fundamental. So you may see that the way the class works and the way the textbook works is you started with the fundamental things. Well, we don't prove that 1 + 1 = 2, but still we start with sets and yeah, linear things, and then we move on to nonlinear functions, and we add up complexity as we move on. So it's the more and more we go, the more useful it's going to feel for you, because you're really going to learn new stuff that's very helpful along the way. Okay. So chapter 8. General functional model. And what I like to call moving dx around. So what's neat about dx is it's a small quantity. It's a infinitely small quantity, but it's still just some number. And like any other numbers in mathematics, so since it's not zero, it's very, very small, but it's non-zero. So we can just play with it and do whatever we like with it, and do a lot of very useful computation with it. So let me start with something. So consider the equation of a solar circle. So I don't know if you remember the equation of a circle. So it's x squared x squared plus y squared. Oh, let me put in r in front. So what's the property of a circle is that all the points x, y are at equidistance from the center of the circle. And now that's what we can do as we did before, is ask ourselves, what if I increase the value of some of the two variables, keeping the other constant? What's going to happen to the radius of the circle? Well, it should increase. So for instance, so let's start with taking the derivative with respect to x. So here, what we're basically saying is, let's assume that r is a function of x and y. So I could have written r of x and y, but, and then I take dr dx, but I'll just leave it at that. So what do I get? Dr dx equals 2x, as I'm sure every one of you knew in advance. All right. So what is this derivative there? This derivative is for every small increase, minute increase in x, what minute increase in r should I expect? Well, it's 2x. So it's a ratio of increase in r with respect to increase in x. But there's nothing wrong with just asking the follow-up question, is simply, what if x increases by some minute value dx? what is the ensuing increase in DR? So this is just a ratio, but what I could say is, oh, I just want not the ratio, but the actual value of DR. Oh, there's, wait a second. Hello. Sorry about that. All right. So this is the ratio. So other questions you can ask. How would R change following a small change in X? And this small change would be dx. What do we have to do? Well, as you can see, we can just multiply by dx on both sides. So to see that. So as I said, dx is just some quantity. We can do whatever we like with it. So let's do that. So I get that dr is equal to 2x dx. And that's it. This is for each minute increase in x, what minute change in r will be resulting for that. So, and then one other thing that I can ask is, I can not restrain myself to a change in x. I could ask the same thing for both. If I anticipate that x may change and y may change, well, there's nothing wrong with doing the same for each. So all we would get is the following. So dr would be equal to 2x dx plus 2y dy. All right. Or more formally, what we just did is the following. So what we did is say dr equals to dr dx times dx plus dr dy times dy. And this is, of course, it would be a partial derivative. And that's what we did there. All right. And this is called the total differential. So let me more formally say what this is. So total differentials. So assume assume the function. So let's start with two variables. So y equals f of x1, x2, then the total differential is dy equals df. So it's 2 x1 minus dx1 plus same thing with the second one. So I can also write it in an easier way. So I can just write f1 and f2. So saying I'm taking the derivative of f with respect to the first argument, taking the derivative of f with the second argument. So let me just say even more. So what's happening there? Well, I'm imagining that y can be affected by many things, and this is a way to synthesize all of the things that may affect y. So what is this? So yeah. So this is changing y caused by or due to x. One, and this is, of course, changing y due to x. Does that make sense? Or does it not make sense? Stop me if it doesn't make sense, but yeah, I think it's after derivative, then it's just a synthesis of using the derivative and then continuing along. So let's just have a small example. So y equals 2x1 squared x2 cubed, for instance. So dy would be equal to what? Can somebody say it?
Be 2x1 times x2 cubed plus 3x1 squared x2 squared.
Almost. Is there's just one thing here? dx1.
dx1.
Yeah, exactly. Thank you. Yeah. So 3. Yes, Azim.
Yeah, sorry, maybe I'm missing the whole point with this question, but I don't understand why we keep the dx. Why do we keep the, like, why do we write, like, doesn't it cancel out usually?
Yeah, so what you could recover is the following. So assume dx2 equals 0. And then what you have is the following. So this is 0. Then you get this. So let's divide by dx1 on both sides. So this divided by dx1 disappears, and this divided by dx1, it's there. So dy dx1 is indeed 2x1 x2 cubed, right? Because that's my initial. So you have to leave it there, because dy, what's the size of this? This is infinitely small. It's a very tiny change. So if you don't put that, then there's no way that tiny change is equal to some x1, x2, that's just some number that's not tiny. So, but if you multiply it by dx1, then yes, this is a tiny thing, and this is a tiny thing. So you have to keep the d's there.
Okay.
So yeah, so another way, so imagine that I'm not dealing with these, but deltas, for instance. So I would have that so.
I mean, intuitively, it makes sense, but on top for our equation where we write, like dr over dx times dx, then in that case, it's canceling out. That's why I didn't understand why we were carrying it forward. But yeah, it makes sense when you explain it.
Yeah, so you can see, for instance, if it's delta. So these are changes, and these are values of function. So this, so if you think about, I don't know, income and asset. So this is asset, this is income, this is income. So these cancel out. So you have to leave everything there.
Okay, thank you.
All right. So yes, let's remove this. All right. So I can have a 3-variable example, but I think you guys are smart enough that you already get it. But imagine that I have some utility function. So we know it's a utility function because that's a letter U, of course. Otherwise, we wouldn't know what we're talking about. Equals to, what did I write? Yeah, 2x1 plus 3x2 plus 4x3. So that's a weird linear utility function. And then how the utility function. How does my utility change? I consume more of 1, 2, 3. So I just take the total derivative. So change in utility is du equals to 2 dx1 here, because the derivative of x1 with respect to x1 is just 1. So dx1, 3 dx2, and then 4 dx3. So makes sense. It's a bit like saying, so this would work with just delta. So delta u is equal to 2 delta x1, 3 delta x2, so plus 4 delta x3. It's since it's linear, it's going to be good no matter how the size of d. But of course, we have if we have nonlinear function, then we need to use very minute changes. Yeah, other utility. Let's use a cup de glace. X2 equals to x1 to the alpha, x2 to the 1 minus alpha. So I get so this is something you're going to do quite a lot, so it's good to see it. So du equals to alpha x1 alpha minus 1 dx1 plus derivative with the second one, so 1 minus alpha x1 alpha x2 to the alpha minus 1 1 minus alpha minus 1, so x2. And then one neat thing here, this is all algebraic, so it's well, like this or like this for that matter. So look what I did here. I've got an alpha that's in front, and here I have alpha minus 1. What does that mean? It's exactly as if I divided by x1 basically. So what I'm going to do is just multiply by x1 and then divide by x1 here. And then multiply by x2 and divide by x2. So that's multiplying by 1, multiplying by 1. And then x1 times x1 alpha minus 1. So that's just x1. Then x2 to the minus alpha is x2 to the 1 minus alpha. And so yeah, let's put the x2 here, the x1 here. Yeah, and what is this? Well, this is the original function I had before. So this is the same as this. So let's put it in front. Yeah, and even what is this? Somebody recognize this? No, doesn't ring a bell. I'm going to point to you in the, yes, it's you, thank you. So it's just you. Yeah, so what's the, yeah, let me just put it this way. Yeah, so it means that the increase in utility from consuming one more unit of good one is proportional to the utility itself divided by the amount of good one I'm consuming times alpha, the importance of consumption of good one, times the increase in consumption of good one. And similar thing for good two. All right. So that's so much things to say about this. It's really what we care about is to have the math under it. So that's what it is. And the rules of, so I'm going to tell you some rules of differentials, but you might guess that since I'm using derivatives to get there, then they're very similar. All right. Given C, some constant. All right. This is not what I wanted. It's better. Constant rule. So DC equals to 0. So if you take the derivative of a constant, then it's 0 because the constant doesn't change. All right, constant factor rule. If I have D CU, then it's equal to, what I can do is pull out the constant, so C times. It's usually what happens. You take out the coefficient. What else? Power function rule. So if I have D to the n, then it's equal to n minus 1. So du. Sum difference rule. UV. Somebody wants to guess what I should get. Oh, yeah, no, sorry, that's the product rule. So sum difference rule is du plus or minus V equals to what? So as in, what do you mean by a numerical example?
Sorry, that was for the YouTube. Yeah, exactly, that one above. But we can do that after. That's fine.
Yeah. All right. So it's just replace alpha by some number like 0.5, 0.5. So you will see that. Yeah, no, you can do it right away. So with numbers. So thing is, so it's always dependent on what the value of x1 and x2 is, but I can just do it for any value. So if alpha equals 0.5, for instance. So then I have that u of x1 equals 0.5. And u of x1 is equal to this. So that's 0.5, 0.5.
Yeah, no, but we have, of course, can take that line as it is, right? We need to derive it. Like we can't just take a over x1 dx1. You would need us to start from the first line to derive it down there.
Oh yeah, but I mean, I did it for any number, so it's going to work for 0.5 as well.
Okay, so we could just, okay, yeah, makes sense.
Yeah,
Okay.
so it would be, for instance, 0.5, 0.5 minus 1 here, so that would be minus 0.5, for instance. So that's a good exercise. It's always good to sharpen your mind by trying numbers and doing stuff. So, all right, so I'll just remove this.
Thank you.
No problem. So do I have a guess for what the rule is here? If I add up two variables, u and v? No clue. Yes. Oh wow! And you also use the. So did you use Unicode in the chat? I didn't know that worked. Nice. So yes, du plus or minus dv. And duv. Oh, compose key. I didn't know that. So if you're unsure, the way to do it is just to take derivatives, and you can know pretty easily what it would be. So no clue what duv would be. Oh, good. Thank you. I'll steal that from you. WinCompose. I didn't know that. Oh, that's a GitHub project. All right. So we have some computer experts in the room. GitHub is a wonderful thing if you understand how it's working. Oops. So no idea, duv? Yes, exactly. V du plus u. And so that's sorry, not the product difference rule. That's the yeah, that's the product rule. Then the quotient rule. So du divided by v is going to be equal to 1 over v squared times v du minus u dv. So it really looks the same. Yeah, and other rules. Are equivalent to rules derivation. But I mean, I'm telling you these rules, but you don't even really need them. All you need to know is how do you get it? It's if you have y equals f of x1, x2, so you take this and that's it. And you apply the differential here, and it gives you this. So that's pretty much all you need to know. Okay. So what do we do with this? Well, I've told you a bit about it, but a very, very useful concept is the total derivative. So that was total differential, if I'm not mistaken. Yes, so total differential. Now total derivative. So it's the same thing, it's just I'm going to divide by stuff. So back to the circle example. With total differential. ER equals to 2x dx plus 2y dy. Then we can ask the following. So a circle usually has its radius not changing. Here I'm saying, imagine that I have this circle and x is not changing and y is not changing and x increases by a tiny amount. So what is going to be the effect on the radius of the circle? But an alternative question I could be asking myself is the following. So given that I'm on the circle, I want dr to be 0. So I want to stay on that same circle with the same radius. But then I can ask myself, if at some point on the circle I was to increase x by some small amount, how would y have to change in response to make sure that dr stays the same? All right, so let's ask. How much if x increases by a small amount, how much must y change in order to remain on that circle? So how would I compute that? What would I have to do? Isolate the dy, yes, and other condition. Yes, okay, I'm assuming that you're saying this whole thing equals to 0. So it means essentially that dr equals to 0. So set dr equals to 0 and isolate y. So I get 0 equals this. So dy, there's a minus sign there. So that's just minus x over y dx. And then follow-up questions. So how would y change in terms of change in x? So that's so I just divide by dx. So dy dx equals minus x over y. So it's a strange derivative because I didn't start by isolating y here. I just thought, okay, let's just use this right away and take the total differential and then set the r equals 0 and then take the derivative. So I get this derivative there. And it's what we call an implicit way of finding the derivative, because I still have a y here. Y is still inside its own derivative, but who cares? As long as I'm on this a point that I know is on the circle, then I can just substitute the value of x, substitute the value of y, and I'm going to get the right answer. Yeah, so this is an implicit way of computing dy dx without isolating y explicitly. Is that how I write it? Yes. So for instance, let's have that and it's again at some point xy, so it's not to know the exact numerical value, then I have to know the exact value of x and y. So if x equals 1 and y equals, let's say, -1, and then dy dx equals -1 over -1, so it's equal to 1. So then I know that if I'm x equals 1 and y equals -1, so I'm on some circle there. So what's going to be the slope of this circle at this place is going to be 1. And what's the radius actually? So that's equal to 2. So r equals x squared plus y squared equals 1 plus 1 equals 2. Would that be helpful if I was to draw a circle? Yeah, maybe let's draw a quick circle real quick. See where we're going with this. So let's do this is our example. So Oh, come on, let me catch that. Yeah, that's hard. Okay. So this is 0, 0. So let's just say x equals 1, y equals -1. So I'm here. This is going to be equal to 1 minus 1. So there's a circle going through this. It's going to be nice if I draw it this way, or no, it has to be larger. Yeah, like this. All right. So that's my circle. And then the question is, if I increase, oh, so let's just put some stuff there, x, y. So if I increase x by a small amount, what should I do with y to make sure that I stay on the circle? Well, I just computed it, that the derivative here is dx over dy. It's equal to 1. Sorry, dx, dy over dx. 1 minus 1 equals to 1. All right. That makes sense? Or if not, you can ask me a question. We're here for that. And yeah, the radius should be, is the radius 2 actually? Or am I completely, oh yeah, no, the radius is, oh, nobody has stopped me. I just made a fool of myself for the whole class, and you just let me go with it. So this is r squared. Oh man, why didn't I see that? So taking the derivative of r, so I would have to take, yeah. Okay, so let me not, oh man, what should I do with that? Yeah, no, I'm just not going to say it's a circle. Equation here. All right. And let's not call this R. Let's call this Z. All right.
Sorry, Professor.
Yeah.
We're still seeing the circle. I don't know if you're showing.
Oh, sorry. Yeah, I'm back in the class now. I'm just going to change a bunch of stuff. Because, yeah, that's sort of humiliating to all right, so I'm just going to say it's Z. But otherwise, I'm going to keep the same, because otherwise I'm just going to confuse everybody. That's not the point. How, okay. Just going to replace Z. Anyways, after the class, I'm going to check if I forgot any R somewhere. DZ. Okay, and I think the rest is okay. In order for z to remain constant. Set dz equals to 0. Yeah, and then if, by the way, it is also the equation of a circle radius rho z. Okay, so that makes more sense. So back to the really sorry, I had a brain aneurysm there. So back to the circle equation. Well, anyways, we were mostly done with it. So this, yeah, the diameter of this is not 2, it's root 2. So it's, yeah, a bit more than, yeah. So you get the point. Still, the derivative still remains. So dy dx at 1 equals this. So here we go. Okay. So where was I? All right, so this is an implicit way of expressing it, but I could also have expressed it in an explicit way. So so how would I do that? Well, I just write z equals x squared plus y squared. And then, so let's just isolate y. So y equals c minus x squared. So y equals to square root of plus or minus. And then here, am I interested in the plus part or the minus part? see what we're doing here? We're expressing y in terms of z and x. But you see that since I have a square root here, I have to use the plus and minus. And you see that y is actually on the, yeah, there's a, it's not exactly a function because this equation could satisfy two values of y for every x. So which part should I use, the plus sign or the minus sign? Yes, good. So since I'm on the negative section of the graph, y equals -1. Let's use the negative part. So I would have y equals minus. And then, yeah, so computing the derivative explicitly. dy dx equals to, all right, so this is, it's always easier to do it this way. So it's equal to 1/2 minus 1/2. Then here I have minus 2x. All right, so I just took the derivative with respect to x. So it's this, I can just put it on the denominator. So that's I like doing this so that I don't get mixed up with square roots, but then yeah, let's re-express it in a neat way. Okay, and so minus cancel out, the 2 cancel out. I get x divided by this. So at so what do I have? X, y, z equals, I said that z equal 2, x equals 1, and y equals -1. So I have dy dx equals 2, this is 1, this is 2 minus 1 squared. So it's equal to 1. Yeah, so we found it, we found the same answer. Thank God. But you see that it's super complicated doing it this way. It's a mess because I have to go through the pain of isolating y, and then, you know, sometimes it may or may not be a function. Here it's not a function, so I have to pick which segment I care about, and then take the derivative. But it's a pain to do it this way. I got this exact same result super easily by just using this total derivative. Dy dx equals -x over y. It's the same result. And what's more, so in economics, since economics is not a super precise science, it's not like we, when we have a model, do we care if it's 2 or 2.1 or 2.2? No. Usually what we care about in our models is, okay, will the unemployment rate go up or go down if we have some intervention on some market? So I have a model of the market, and then I care about what's the more or less the trend of the that the market is going to take. So I'm looking at the comparative statics, and I care, is the derivative positive or negative? So if I just care about the sign, then again I can just stay here. I stay here. I have dy divided by dx equals minus x over y. If I know that this is negative, this is positive, then I know that the derivative is positive. Usually that's where economists stop. They don't really care about having the exact value somewhere. It would be better, but we are cognizant of the limitation of our discipline. So what we want is a picture of what's happening in our model. And the model may be a complicated model with 10 variables. And at some point you care about, okay, how is, I don't know, employment going to change if export rises or if the interest rate goes down or this kind of thing. So we just take the total differential and we take the derivative of the variable we care about with respect to the other variable that's changing, and it gives us right away the right answer. All right. So where was I? Oh yeah, so let me just have, so what time is it, by the way? Yeah, 11:05. Okay, so in general, so this is just a general way to obtain a total derivative. So given a function f of x, y, and maybe other things equals 0. So if I have something equals something else, then I just take everything on the right hand side and put it there. So you see that I can always obtain this this form of an equation. Then we can have, we find the total derivative. Dy dx by, oh yeah, and by the way, I'm going to be a bit more specific here. So the way we write this is the following way. Yeah, no, this it's going to be complicated to write it. So just dy dx, keeping variable constant by, so 1, computing the total derivative, with respect to x and y, so here I would have if I have f of x, y, and other stuff equals 0, what do? I take f x dx plus f y dy. So this is the derivative of f with respect to x, derivative of f with respect to y, and then I set that equals to 0, and then 2 collect terms in dy on the left and terms in x on the right. So here I just going to write it this way. And then 3 divide by yeah, what I want is dy dx. So I divide by fy and dx, yeah, fy dx. If, of course, so dx is a small quantity, but that's non-zero. But of course, if fy is not 0, then I get this. So that's a nice way to get implicitly the derivative. So just before finishing, I have another quiz. This one is a bit more complicated. So yeah, but what could I do? Yeah, let's go on and do the quiz. If I can find it. Oh. Here it is. So quiz on total and total derivatives. So that one you really need a pen and pencil and paper. It's a bit longer, but yeah, well, you can start, and if you have questions, you can ask me. Let me check again my questions to make sure there are no problems with this one. And if you are struggling with the last question, it's normal. I put it there to see if you can think on your feet and think a bit ahead. So, but don't worry, it's not because you didn't understand what we were talking about. It's because I haven't talked explicitly about it. And please ask me questions if you're stuck or if you're not sure. Yeah, I want to check my answer to make sure that. So I'm going to unshare my screen for a bit. Make sure I didn't mess up. Time to be lost. You're lost. So you just have to use the rules of derivation or the use of differentials. So are there other people that are a bit lost? Yeah, so what is the derivative of, oh, I didn't tell you what so what is the derivative of log? So it's going to, the derivative of log is, yeah, so ln of y plus z equals to 1 over y plus z times, and then if we care about both, it's dy plus dz.
We can't see your screen.
Yeah, no, I'm writing it in the chat.
Okay.
Yeah, so if I have a log of natural log of y plus z, so it's 1 over what's inside, so 1 over y plus z times the derivative of whatever is inside, so dy plus dz. It's like if you take the derivative of log. Yeah, also I'm going to add that in the rules of differentials. Okay, I'm happy I didn't mess up. Yeah, it looks like we won't have time to. Is there some uncertainty about what you have to do just before we finish the class? Otherwise, you can finish it on your own. And then we're just going to discuss the result next class. All right. So sorry for having messed up this this R thing. I really, my brain just maybe it could have been done if I used the square root everywhere, but I don't know. So all right. So next class we continue here, and yeah. So have a nice weekend. Oh yeah, the result of the exam are going to be posted.
Professor?
Yeah.
I just had something to say, but it wasn't. It didn't have anything to do with the class. I don't know if you're still.
So let me just, if you want, if it's more private, I'll just finish the recording now, and we can hop back in right away in like 1 minute. Maybe.
Yeah, sure. Okay, sure.
Okay, so same link.